Hello everyone, welcome to Basics e-learning.
ZTransforms is one of the most important topic in signals and systems and also in signal processing subjects. The video series that I am going to make on ZTransforms will give the student a very clear understanding of the topic. In my previous 15 videos, I have discussed signals and systems basics, which covers almost module 1 completely, irrespective of the university to which the student may belong to. I'm going to leave a link of that playlist in the description box. Please check it out. Now, in today's video, lesson number 1, I'm going to give a brief introduction on Z-transforms. The topics that I am going to cover in this video are: what is a transform, why do we need a transform, introduction to Z-transforms, and where we are using this Z-transforms, how the Z-transform is defined, what is the famous region of convergence that we are going to use in the entire chapter, what is a finite duration sequence and infinite duration sequence. Let us see what are these transforms. By this time, you might have heard about many words like Fourier transform, Laplace transform, Z transform, fast Fourier transform, discrete time Fourier transform. But what is this transform mean? So the transform is used to change the domain of any given signal. So it is basically a mathematical tool that is used in signal processing. So the meaning of this statement is, you have your signal can be drawn either in the time domain or in the frequency domain. So to convert or to change or to transform the signal from time domain to frequency domain or from frequency domain to time domain, we are using these transforms, right? But why do you want to change the domain of the signal, that is from time domain to frequency or frequency to time? What is the purpose? Why we are using? So here, these are the advantages of applying transforms on any basic signal. For better understanding of the problem, sometimes the signal may look very clumsy in time domain. So if you convert that into frequency domain, it may be better understandable, easier analysis, and to make some calculations easier, numerical analysis of data. Suppose we are multiplying, if you want to multiply two signals in time domain, the process will be very difficult if you have ramp in the signal, right? I think we have already discussed multiplication of two ramp signals, right? So the process is very difficult. But if you convert it into frequency domain, here that will be very easy. Similarly, the convolution in time domain is very difficult. By the time it goes to frequency domain, the convolution becomes multiplication. So again, the signal processing, it will be very easy. So for that purpose, they are using these transforms for analyzing the signal in an easier way. Coming to Z-transforms. Z-transforms are used for the study of discrete time systems that are described by a linear differential equation with constant coefficients. So this Z-transform is the discrete counterpart of Laplace transform. So you might have studied about Laplace transform, which is defined as S is equal to sigma plus j omega, right? Where sigma is the real part and omega is the imaginary part. So here also the digital or the discrete conversion of this S is Z here. That is, the Z transform is used only for discrete time signals, whereas the Laplace transform is used for continuous time signals, right? Now, coming to the definition, as I am telling, it's a discrete time signal, n will come, right? That is, if you are considering discrete time signal x of n, then the transformation of that signal, that is the Z transform of that signal, is defined as x of z. X of z is equal to sigma, n is running from minus infinity to infinity, x of n z power minus n. That is, the signal x of n is extended from minus infinity to infinity. So whatever it may be, the signal that is extended from minus infinity to infinity, the whole plane converted into z plane here. the full signal is converted into Z plane. Now, the next important term is region of convergence. The set of Z values for which the summation converges is called ROC. So if you observe here in the formula, there is sigma. Sigma stands for summation. So in continuous time signal, you will be seeing the integration symbol. Here it comes to sigma as it is a discrete time signal. So you will have the instances. So all the instances you will be adding, that is sigma here, right? So the summation, where the summation converges on the Z plane, when you are converting from the time scale to Z scale, right? Wherever the summation converges, only that part we call it as region of convergence. So generally it is defined as the annular region of the entire complex Z plane. So annular means the region that is between the two concentric circles, we call it as annular region. So you have a lower limit and the upper limit. The region defined by the lower limit and upper limit. The region bounded by the two circles, we call it as region of convergence, where the x of n exists in the Z plane. So that is defined as region of convergence. Z-transforms and ROC of finite duration sequences. There are three types in this finite duration sequences: right-sided sequence, left-sided sequence, and double-sided sequence. So as I have explained earlier, the signal is defined for x of n is defined for the interval of minus infinity to infinity, means it is an infinite duration sequence, right? So if it is an infinite duration sequence, every time it won't be extending from minus infinity to infinity, right? It has certain range. So that is called a finite duration sequence. It has a range, that is the lower bound and upper limit. Upper limit and lower limit, if a signal is existing with both upper and lower limits, then we call it as a finite duration sequence, or either the upper limit or the lower limit. If it is limited by one side also, then we call it as a finite duration sequence. Coming to right hand side sequence, as I am telling, the signal is extended from minus infinity to infinity. This is the right hand side and this is your left hand side. If the signal exists only on the right hand side, then we call it as a right-sided sequence. That is, the signal extends only from 0 to infinity. Then we call it as a right-sided sequence. Means x of n is equal to 0 for n less than 0. See, this is your n, right? This is the scale, n is equal to 0 is the midpoint, or you are taking that origin as the reference. N less than 0 means left side. N greater than 0 means towards your right side. So the signal right-sided sequence or the right-sided signal is defined as x of n is equal to 0 for n less than 0. But for the positive side, you will be having the signal, right? So x of n is equal to 0 for n less than 0. Also defined as your right hand sequence, or else, see, suppose if the signal is extending in this limit, that is also only right hand side signal only, right? So that can be written as x of n is equal to 0 for n less than n naught, generalized, where n naught is a positive integer. If n naught is equal to 0, this case will come, right? So extremely fully covered with the right hand side only. So x of n is equal to 0 for n less than 0 is defined as the right hand side sequence. So if you remember, this is called the causal signal, right? So I have discussed in my previous videos also, if the signal exists only on the right hand side, then we call it as a causal sequence or a positive time sequence. Now, what will be the region of convergence for this right-sided sequence? So, this is your Z plane. If you imagine, this is your Z plane. As I said, it has lower limit and upper limit. So, lower limit and upper limit. Let us say the lower limit and upper limit are R1 and R2. That is, the signal is extending between R1 and R2, right? So the signal converges in the region of R1 and R2. Here, the lower limit is restricted as it is a right-sided sequence. Here, the region of convergence here is like this. See, region of convergence is entire Z plane except at Z is equal to 0. So you can write this as entire Z plane except at Z is equal to 0, as this is a right-sided sequence. Means, example, the right-sided sequence will look like this. See, x of n is equal to 1, 2, 2, 1. See, n is equal to 0 is here. Means the signal is extending only on your right side. Means looks like this: 1, 2, 2, 1. Right? So this is your x of n. Whenever you see such type of signal, this is only right-sided sequence. Then what about your x of z? As I have defined, x of z is sigma. N is running from minus infinity to infinity. Here, depends upon the signal range, your n limits will change. X of n, z bar minus n. Suppose, see, if you are talking about this signal, the signal range is 0, 1, 2, 3, right? Lower limit is 0 and upper limit is 3. So that can be defined as n is equal to 0 to 3, x of n, z bar minus n. This is your x of z, right? So like this it can be defined. So this is all about right-sided sequence. Coming to left-sided sequence, again take here t, this is 0. Generally the signal can be extended from minus infinity to plus infinity. Left-sided means the signal has to exist only on the left hand side of your time scale, right? That is in the region of 0 to infinity anywhere. So the signal here is defined as x of n is equal to 0 for n greater than n naught, right? So that is towards this side, anywhere n naught, here and all, if it is 0, only the signal if it is extending left side, then we call it as a left hand sided signal, right? So suppose if this n naught is here less than or equal to 0, then what is this? The signal is an anti-causal signal, right? As I have already discussed in my previous videos about causal and anti-causal. Do check. Now, for this type of signals, what is your ROC? Here, ROC is defined as entire Z plane except at Z is equal to infinity, right? Now, the signal, how the signal looks like? X of n is equal to, suppose, say 1, 2, 2, 1, and this is your signal. See, now this is n is equal to 0 marking. So the entire signal is on the left hand side. See, like this it looks like, right? At n is 1, 2, 2, 1. This is 0, minus 1, minus 2, minus 3. So generally the signal is defined as n is equal to minus infinity to infinity. Right? Now the limit is changed from n is equal to 0 to minus 3. Right? Sorry, n is equal to minus 3 to 0. The lower limit should be minus 3, no? So n is equal to minus 3 to 0, x of n, z bar minus n. Right? So this is how the signal is defined for left-sided sequence. Coming to double-sided sequence, the signal exists on both the sides of the plane. That is on both the right hand side and left hand side on the n scale or the time scale. But here we are talking about the discrete time only. So this is n, right? So if it is existing on both the sides of the plane, then we call it as a double-sided sequence, right? So the finite duration in both left side and right side, that is, it is restricted on both the left and right, right? The boundaries are defined on both the sides. Then we say it is a double-sided sequence. So the ROC comes to except at z is equal to 0 or z is equal to infinity, right? And right, x is equal to, z is equal to 0 and z is equal to infinity. Except these two, the entire Z plane is the region of convergence. So the signal looks like this. See, x of n is 2, 1, 1, 2, somewhere here n is equal to 0, right? So the signal exists both on the left side and right side. See here, this is 0, x of n, right? So at n is equal to 0, you have amplitude of 1. This is minus 1, minus 2 and 1. At n is equal to minus 1, you have an amplitude of 1. At n is equal to minus 2, you have an amplitude of 2. Whereas at n is equal to 1, you have an amplitude of 2, right? So the signal range is from minus 2 to 1. So this can be defined as x of z is defined as n is running from minus 2 to 1 x of n z power minus n, right? So the limits are both the sides, they have restricted here. And the last topic is ZTransform and ROC of infinite duration sequences. Again, they're explaining three types in infinite duration sequences also. Positive time exponential sequence, negative time exponential sequence, and double-sided exponential sequence. Coming to positive time exponential sequence here, it is defined as x of n is equal to a power n u of n. See, u of n, you know, that's a unit step signal. U of n is equal to 1 for n greater than or equal to 0, right? So that means x of n is equal to a power n for n greater than or equal to 0, and it is equal to 0 for n less than 0. So x of n is equal to 0 for n less than 0. So this clearly says the signal exists only for n greater than 0, means on the positive side on the scale. So that's why this is called positive time sequence. Coming to the word exponential, see, a power n, right? So this is nothing but the exponent, means as the value of n changes, the value of x of n also changes. Suppose if n is equal to 1, it is a power 1, then a power 2, a cube. Depending upon the n value, x of n value also changes exponentially. So that's why this is called positive time exponential sequence. Coming to ROC, the region of convergence for this type of signal is mod z greater than mod a, as it is a positive side sequence. So mod z is always greater than mod a. So the derivation along with the explanation here will be given in further videos for this. Coming to negative time exponential sequence, the x of n is defined as minus b power n u of minus n minus 1. See, we know u of n is a unit step signal. U of n is equal to 1 for n greater than or equal to 0. Now define for u of minus n minus 1. That is also equal to 1 when minus n minus 1 is equal to greater than or equal to 0. See, this type of explanation is given in my previous videos, like unit step signal, right? So that I am going to give a link in the description box. So first go through the basics, then you can understand Z transforms very easily. So minus n 1 minus 1 greater than or equal to 0 means here minus n is greater than or equal to minus 1. N is less than or equal to minus 1. So u of minus n minus 1 is equal to 1 when n is starting from minus 1, right? So minus 1 to infinity, you will be having the signal. Otherwise, towards your right hand side, there is no signal. It is 0, right? So this is u of minus 1 minus 1. So u of minus n minus 1 is defining that the signal is a left-sided signal or negative time sequence. Now, exponential, as I have given the previous signal also, minus b power n is indicating your exponential signal. Then what happens? X of n is equal to minus b power n value for n less than or equal to minus 1 and is equal to 0 for n greater than 0, right? So this is how the negative time exponential signal is defined. The ROC of this signal is given by mod z is less than mod b. So as of now, you just remember like this. I will give you a brief derivation in my next video. See, mod z less than mod b means you have to draw a circle with radius b here. So the region of convergence is mod z less than mod b means this region, right? So like this, the ROC is defined for this negative time exponential sequence. Coming to double-sided exponential sequence, it's a combination of both positive and negative time sequences. The sum of positive time exponential sequence and negative time exponential sequence gives you the double-sided exponential sequence, defined as x of n is equal to a power n u of n minus b power n u of minus n minus 1. That means the signal exists on both the sides. So this side also u of n means from starting from n is equal to 0, right? So like this. U of minus n minus 1 means from minus 1 to minus infinity. So the signal exists from minus infinity to plus infinity. That's why this is called infinite duration signal, right? So now both the sides it is exponential, right? So the signal exponentially decreases on your increases on your positive side and decreases on your negative side. Sorry, this side, yeah, b power minus 1, b power minus 2, like that. So it will be exponentially decreasing, right? So both the sides, it's an exponential sequence. So that's why this is called double-sided exponential sequence. Coming to the ROC, ROC is defined this as mod z greater than a intersection mod z less than b. That is again the combination of the positive side sequence plus the combination of negative side sequence. That is, you will have an annular region. So mod z, take a circle of a, right, with radius a. So your ROC is mod z greater than a means entire z plane after this circle, right, after this a. So this full portion will be your region of convergence. The region of convergence will be the entire z plane except this circle of radius a. But here mod z less than b. So you will be having another circle of radius b here. So this is mod z less than b means only this portion, right? So this annular ring portion only converges for this double-sided sequence. So this is the ROC of your double-sided exponential sequence.
For more videos, please do like, share, subscribe to our channel. Let us know your suggestions and queries in the comment box. Thank you.